Okay, this is an updated program showing what happens when we have a lot of emitters and a lot of detectors. So here, there's 5 emitters and detectors. Red is an emitter, green is a detector. And really what I'm interested in is what we call the pattern of overlaps. So what it's looking for is the isoclines. Isoclines are for every given emitter and detector pair. And there's 25 possible emitter and detector pairs in here. There are certain places that this could be, and the isocline is the sum of all those possible places. So for these two, anywhere that's the same color, the emitter and detector can't tell the difference, so it doesn't know where it is in that isocline. And I can pick multiple ones, so I can say, like, okay, from this emitter to this detector, show me where those isoclines are. And everywhere, like in green, for example, looks about the same to that particular emitter-detector pair. So when it comes to finding a location from a bounce sensor, what we look for is intersections of different isoclines from different sensor pairs. So there's 25 different ones. We want to see where we have intersections of all 25 isoclines. And if we find that, that tells us, okay, I think that's our given spot. So what's going on here, the more isoclines there are, the brighter the point is in green. And if you look up at the top, this shows you how many points it's found that have the maximum possible matches. That means that are on all 25 possible isoclines. So one thing you'll see is as I go up, the match points, so once I get past this point, that's where I stop having perfect precision. Now, a couple things there's a few things that are kind of counterintuitive to me. So one is adding more sensors doesn't improve that. I am still, unless I change my tolerance, that is my sensing tolerance, I'm still somewhere on this isocline map, but that doesn't reduce the number of isocline points. And similarly, changing the spacing of sensors, I thought maybe having the sensors the emitters and detectors evenly spaced would make a difference. But no, that also doesn't really have an effect on here. The thing that, it doesn't have a bad effect, it just doesn't change the numbers. The thing that I have to do if I want to improve the accuracy is I have to tighten my tolerance. That is to say, I need to have better sensing resolution and I need to discriminate more about where my isoclines are. And now, as I do that, so now I cut my tolerance in half. And really, the acid test, because this is an R-squared issue, so as I get further and further away, I start to get more and more and more points all in the same isocline. So I have to tighten up that tolerance. And the question is, we say, well, what's the maximum sensing range? What's the furthest I could be from my sensors where I want to get a good value? And we find a tolerance where I can read that. And if I tighten that up for a value out there, that's going to work everywhere else on the map. I have to set it for the hardest spot to find. The problem, of course, is getting really tight tolerances like that is really hard. We're gonna have to work like crazy to get that tolerance from a hardware point of view, to get that kind of tolerance. So another question, like the other obvious way to do it, if you want to limit how tight your tolerance can be, is just get closer. Don't have your range be fairly short. And as long as you set that, you can loosen your tolerances more and more and more, up to the point where it's fine. If you can't handle loose tolerances, the other possibility is that you just have a bunch of points on your isocline. So to give you a sense just of the relative scale here, we're looking at points that are like roughly the same diameter of the emitter and detector. And what that's telling me is, well, imagine that I have a sense bar right here, and I am this far above the sense bar. Maybe I can't localize down to a 1 millimeter by 1 millimeter area. Maybe my area is a square centimeter, and then we can run an averaging function over that to figure out where it could be. So I think the way to kind of approach this design is somewhere in here there's a smart thing we could do, which is we could build lookup tables for what the possible locations are for a given value, like a given brightness value on each of the detectors. And those lookup tables need to point us to will tell us, okay, this is that isocline for that detector. And then we have to have some clever averaging for looking at multiple isoclines. So like here we have 7 different points that all look like they're intersections of an isocline. How do we smartly boil that down to 1? And how do we do this on a $2 chip too, is another question. So that's the best simulation I've got so far. It's neat, it's promising. And one last thing to note about this is for isotropic emitters and detectors. And as I mentioned in the previous video, we're not doing isotropic emitters and detectors. These are real world things, so they all have a certain value. And my hope is that'll help us limit where things can be on an isocline, but I'm not sure that is going to end up being the case. I'll try to model that next.